Tonight we have with us Paul Morgan, who's going to be talking about Eva Creek and its first year of operation and how that's going. Paul has been with the energy industry for 36 years and with Golden Valley 22 of those years. He's the one that keeps the lights on at my house and runs pretty much all of their generating assets except for the coal plants down in the Healy area. As fascinating as this lecture is, I would ask that we end and clear the room at 7:30 because there's a movie here tonight, and of course we're always happy if you guys stay and watch the movie for our friends at Blue Loon who make this facility available to us every month, and we're very grateful for that. So with that, I would ask you to silence your cell phones, and here's Paul. So thank you and good luck.
Thank you very much. Wait. Good evening. Silence my cell phone. That's a good idea. All right. Small buttons. Okay. Well, here we are. We have been running Eva Creek for a little over a year now, and we have our first year's data, and it's fascinating. So this is what it looks like at Eva Creek. These units are pretty tall, but they look a whole lot taller when you're looking down. It's not that I've climbed them. It's 280 some rungs. That hub height is 262 feet. That is a long ladder. You can see that bug on the lower blade there is in fact Spider-Man checking out the blades for any damage after transportation. Okay, now we placed Eva Creek. Initially, we had no idea where to put a wind farm. We were looking around for where might be a suitable site anywhere in the interior here, and of course it would be best if it was closest to an intertie. The line losses connecting a wind farm to an intertie are one of the biggest losses, and it's extreme expense in adding intertie to connect to a wind farm. So this one couldn't be any closer. We actually have wind turbines on both sides of the northern intertie. And we went looking. The meteorologist said that what you really need is nice rounded hills, And they said that these hills here were actually the best hills for a wind farm, but that green color indicates that they're in Denali National Park, so we didn't even ask. There's our first Met Tower, 100-foot Met Towers, one of 7 that we installed down there. The later ones were hub height, 80 meters tall, and even those 262-foot tall Met Towers are stood up just with a hand crank pulley. It's quite a process. We learned a lot with this one. The first one that went up, we put it exactly the wrong way with all the sensor booms were pointing just exactly downwind of the predominant wind, so it wasn't the best move. But we do have a tremendous amount of data for the site because the site was kind of on and off and on and off. There was no time when it really looked like it was going to happen up until the last 5 minutes when it finally did. And so we just kept gathering data, so we ended up with about 8 years of data before we proceeded. That's what it looks like up there. It's really a spectacular location. So the turbines that went in were repower MM92s, the 92 being the meters diameter of the rotor. The CCV is the cold climate version, and they're all called WEX, wind energy converters. These things produce a little over 2 megawatts, and they produce full power at 28 miles an hour, and they cut in at 6.7 or just below 7 miles an hour, and they cut out at just below 54 miles an hour when they have to shut down for their own protection at higher speeds. And we have had plenty of times when we had to shut down because there was too much wind. They are definitely enormous, and the swept area of 1.66 acres I mean, I live in a little 1938 house in downtown Fairbanks. It's on a 50 by 100 lot, so this thing is like a subdivision on a stick. It's a pretty substantial size. The most impressive, after all the years working on it, it's really quite something to go out and see them standing there. Repower, the manufacturer, changed their name just last month to Senvion, and so I guess they had licensing issues with the guy that owned the name Repower. Now, the capital cost of Eva Creek, about $94 million. Of that, 13.6 was different grants. And what really made the project fly was the fact that we came up with this very cheap money, just over 1% financing. And these were renewable energy bonds. And of course, Golden Valley is cooperative, so we don't actually pay tax. And so the production tax credit, which is what inspires a lot of wind farms for profit companies, didn't make any difference to us because we weren't paying any tax in the first place. So we were lucky to get these renewable energy bonds. They came out a few years ago, but in very, very small amounts of money that really wouldn't be enough to swing a farm like this. But finally, we were able to get sufficient funds. So this divides out to about 8.7 cents a kilowatt hour, exclusive, in the big red letters there, of regulation cost or load following, which no wind farm runs by itself. It has to have another power plant running alongside with it. And a fair bit of this talk is about what it takes to load follow. So a load following power plant is one that adjusts its output as the need for power changes during the day. And of course, people go home, they turn on, devices at home, the need for power goes up. People go to bed, the power goes down, comes up again for breakfast, down during the day, up. And you have to always have some power plant that is following that. But this difficulty is compounded by having a wind plant because nobody's controlling that. There's nobody sitting there with their foot on the gas of a wind plant, so it can ramp up and down 20 megawatts in just a few minutes. And if your wind energy is dropping when your grid requirement is increasing, then it can exceed our capacity to slow a power plant down or speed it up enough. Now this curve I entirely made up with Excel. It's not a real curve at all, but it's just to give you the concept of a load following situation. The green is the output of the North Pole expansion plant, which is our load following plant most of the time. What we have to do is estimate each day how much power is going to be used for every hour of the day, all through the day, and we buy a chunk of that from the gas power from down in Anchorage. They are very fussy about how much power they actually sell to us, because they in turn specify to the gas companies how much gas they're going to need for each hour during the day. And if they vary by some very small amounts, only 1% or 2%, there are some significant financial hits against them that are built right into their gas purchase contract. And the gas sellers they're in a lot different position than they were years ago, carry a lot more authority. So that blue is our guesstimate for the day. The green peak is, there we go, the green peak is the actual load during the course of the day, and then the red is what Eva Creek is producing, and of course this is going up or down as there is wind or isn't wind. And so at some times there's a lot of load following, and at other times not very much. And these plants have a little trouble going to meet some of the lower loads, and of course they run out at some point and you have to start another one. Okay, so we'll look at the performance figures for Eva Creek for 2013, and we have 3 measures: the output, obviously how much it made, and net versus gross is just how much any power that we didn't take from the site because it was either used there or we intentionally let it bleed off. That would be the power produced and the net is what we actually get. I should stop kicking this microphone stand. Capacity factor is how much it runs relative to how much it could run. And so, if it's ran a full load 100% of the time, that's 100% capacity factor. I've got a slide which will show this reasonably well. Availability is more of a maintenance type view. If it's available to run in the first place, then that's our availability percentage. There can be times when work is being done to a tower so it's not available. However, if the wind is not blowing, we're not actually losing anything, but we still count that as not being available. So availability is any time it couldn't run, regardless of whether or not there would be wind to drive it. This is the daily performance curve for last month, for January. And actually, there is a 31st there, but it's so low, it was like 1,200 kilowatt hours. But you see how from day to day, there's radically different performance out of it. I drew that red line way up on the top there. That would be 100% output for the day. So this tall line here would be 75, heading for 80% capacity factor for that day. Whereas this one would be, perhaps 10% for the day. And we average it out, and that month was about a 40% capacity factor. And what we had predicted and have indeed found is we have considerably more wind in the winter, and it's an S or sinusoidal curve with low in the summer and high in the winter, which is just perfect. That's when we need it, so that's a pretty good deal. So here are the 2013 performance figures. You can see that availability was pretty good. It was only 1% of the time on average when it wasn't available. We had the capacity factor, which in May got as low as it ever got, less than 20%, and in October, above 50%. Radically different performance. Added up to obligingly round numbers, 33%. Now that's 33% net. That's actually what we took away from the site. It did actually generate more power than this, and I'll explain that in a little bit further. So we have a 99% availability, which means the units were very reliable, and we had very few issues with them. You can't really argue with a 99% availability. The 33% capacity factor with the component that we didn't actually remove from the site is in fact exactly what we were expecting. The total production of 71 gigawatt hours, if we look at that in terms of homes supplied power by Eva Creek, the average electricity bill now around Fairbanks, 660 kilowatt hours a month. So that would be almost 9,000 homes, their power for the entire year, which I think is pretty impressive. Okay, more charts. I can't help it. I've got to do charts. This is the availability chart, and it doesn't actually, missed it. It doesn't actually start until 94%, so you're only seeing the very top of it. We had this 1 month, 96%, and that was because we had a frequency converter choke blowout, and we have a range of parts which we bought for the site, and there's a pretty large fleet of these units. There's 9,500 of these things knocking around, and statistically there's a good basis for stocking whatever you stock, and so we went with what was likely to break, and something else broke. That's the way of things. Net output in megawatt hours, we can see our low month in May and our extremely high month in October. Capacity factor, of course, really is just a different view of the output. Well, actually, I should look at that a little more. That we were predicted this sinusoidal type curve, and it means that October was really exceptional month. It had a lot of output that month, and more than we would have expected. So we would expect to have shaved that off, in here somewhere, and we would have expected November and December to have been higher up. And so every month seems to throw a curve at you. Remember November, that was when we had the big storms. We had a lot of time where there was just more wind than we could handle, and it had to shut down for its own protection. And then we got icing to round it off nicely, and in December we had the one fault and a lot more icing. The December and November, because these units, they weren't all in use, but the year before, no icing. This year, icing. There is a substation up at the wind farm. 3 years ago and 2 years ago, no snow. That's why we put it there. There was no snow. Last year, there was this much fence sticking out the top. A caribou could have walked over into the substation, and so there's definitely variations that are significant from year to year. So I said that we actually had more power generated there, and we used a V-bar meteorologist to estimate how much wind there would be, and they predicted this much, and we got, I've got those the wrong way around. They predicted this much, and we got that much, so we were 0.1% above their estimate, which was pretty good going, and they allowed for icing and everything else. And I was explaining to Brent before that there are different types of meteorologists, and we did use both, the pure science guys and there's the voodoo guys, and V-bar are the voodoo guys. They go crawling around on the ground and they look at the weeds and they sniff the air, and all this stuff, and they were the ones who were just absolutely on the money. It was very impressive. Actually, they had variations from quarter to quarter, but it seems like if you don't get it this month, you get it next month. It's you get the same amount in a year pretty much, even if it shifts a bit. Yeah, there we go. Okay, so we have learned a considerable amount about icing. When we first started up, I should mention that Senvion, when they first put in these units, they didn't actually have any in icing locations. They had the cold weather variant designed, but they got contracts for us and a much larger wind farm in Canada at the same time, and they have both gone in. And when originally they had icing, the control algorithm called for any kind of sensing of icing would cause the unit to shut down for 120 hours, 5 days, hoping that it would then be gone. And now we have a whole hierarchy of, well, not a very tall hierarchy, but we do have a hierarchy of responses where we reduce a little when we sense a little, and then we reduce more, and we're on about our fourth version of the control software already, as we learn from these two wind farms how we can handle the icing. So, of course, the primary concern is that if you build up a lot of ice on a blade, particularly as if it's just coming up to top dead center, it can throw that ice more than 1,000 feet. And, you're talking about something that's at least the cross-section of a bus, so it's definitely of concern. But for that location, it's pretty handy because there's no housing anywhere near. There's no highways, so it's pretty well out in the sticks. There is actually no road access there. We get everything over on the railroad and have to have vehicles on that side of the Nenana River, so that takes care of getting whacked by ice on the whole. The secondary concern is that you would have an out of balance. You'd shed the ice off of one or two of the blades, and then the third one would obviously give you a little excitement. And so, hitting something with the ice, then damaging the unit, and then thirdly, of course, the loss of any power, because you're not producing optimally if you've got any kind of change in the cross-section of the blade. And our guess is that it's somewhere between 1% and 3% loss due to icing. Now, this picture was actually taken about 11 o'clock this morning, and we have a classic spinning anemometer with the little cups on, and you can see that those cups are full of ice. And this one is a sonic variant. And so the first level of control is that if this one is saying, oh yeah, 20 miles an hour, yeah, 20 miles an hour, no, that's not windy. You get a variation between the two anemometers, then we can say right away, oh, well, that's probably icing. It may be a bird standing on the anemometer, but it's more likely to be icing. This, by the way, sits on top of the nacelle. So somebody has climbed up 280 rungs and is looking through the hatch at the top and took that this morning. They took a camera with them, but it iced up before they could take a picture, so that's from the cell phone. So phase one is where you see the difference between the anemometers, and we reduce from the 2.05 megawatt maximum output down to 1.5. Phase two is where we have an anticipated power curve. So for that sonic anemometer, we should be seeing this amount of generation, and we don't see but a fraction of it. That straight away says that you have a huge amount of icing, and so we bump the unit completely offline, and we leave it off for 8 hours. And then we give it a little test start, and if it's still iced, we go another 8 hours. And at that site, we do have the temperature inversion there, and so we don't really have times when there's not some reasonably warm weather coming. We have a lot of warm air coming from the south side of the Alaska range, and so it does relatively quickly de-ice these things. I mean, sometimes you can, I'm sure we could be iced for a solid month sometimes, but I think that would be unusual, and it is quite common that we would ice up in the morning and de-ice in the afternoon. And what we don't have, because of this different variation in the anemometers, is we can't tell how much generation we would have got had we been online. So we don't have a good feel for what we're losing through this yet. I mean, what we probably need to do is get an extremely strongly heated anemometer, which just won't ice, and that would be then our reference. There are currently existing superhydrophobic coatings, and they don't allow, if you drop a drop of water onto something, it spreads out and you see the meniscus around it. Well, it sits as a bubble on top of anything with a superhydrophobic coating. These are nanotechnologies, and they work really great, other than the fact that they come off after 2 weeks or a year. It's not long enough, that they shed the ice and they shed the coating with them, which is a bit of a disadvantage. As painting those things, every 3 weeks, not so much. However, that's where we're going. That seems to be the most intelligent solution. Rather than heating, I mean, there's different technologies used in aircraft. Inflatable coatings, which you can blast the air into and shed the ice off that way. You could heat them. If you had heating, it would be the very outer tip. And then, once you'd heated all 3 of those and were quite confident they'd melted off, then you could heat the next band in. But it would be a huge amount of power heating that amount of floor space. So to explain the generation application, generally Golden Valley or any utility runs the cheapest thing first. And obviously that's things with no fuel. And the wind farm is in a tricky position because it can't run by itself. It has to have a load-following power plant in order to be able to run. Because if you're going to achieve a steady load, if the wind drops off, something else has to pick up. You've constantly got to be able to adjust to produce the same output all the time. So our first choice for running, if we can get it, is the Bradley Lake Hydro. It's somewhat trapped by the intertie system down there that sometimes we don't have access to the power, so we have to take it at times which are not necessarily convenient to us, but nevertheless, it is cheap. So the next thing is the gas power from the Anchorage utilities, followed by the Healy coal plant. But what's happening is the Anchorage utilities are charging more for wheeling, and the costs are going up as they're facing them themselves. The cost of gas is going up, and we're right at the cusp now where the Healy plant will actually be cheaper than the Anchorage power anytime. No, I don't know quite when, but sometime here shortly. Then after those, this is our normal stack that we would run, these bottom ones here, and we are using the combined cycle plant at North Pole for load following to adjust its output based on what the need for power is. And then, of course, it's now running in conjunction with Eva Creek. Generally, these top ones, the older units, are not running because they're less efficient and more costly. The frame 5s are about, we're talking about a 50-year-old design. These are about 24% efficient. The North Pole frame 7 units have regenerators on them. There was a new regenerator put on last year on one of them, and so that one's about 38% efficient. The older one is 37% efficient. Whereas the combined cycle plant, depending on these numbers vary a lot, and it's based on full load, the maximum output, but the combined cycle can be 52% efficient, a little over 52%, and that's right up there in gas turbine terms, that the most efficient in kind of lab-type environments, gas turbines are still scratching at 60%. So that's a pretty efficient unit. So this is the hierarchy. We run the cheapest thing first. The hierarchy would change if fuel gets more expensive or less expensive, so it's just wherever the dollars are. Now, we do have regulation issues in that we have to schedule the power a day ahead. And so, if we're not quite right, in any estimate, you might have noticed, may vary from reality when you get there. We're never quite sure. We may have to start a second gas turbine, or we may have trouble getting the combined cycle plant to go low enough. And other utilities have wind turbines in their areas now, and everybody has to keep a plant to load follow those wind turbines. So they would have been selling us that power at one time, and now they can't. They've got to keep it for their load following. They have to keep this buffer. So it's an effect that we didn't really think about up front, but that's the reality. And of course, the coal, and particularly the coal, but the combined cycle plant too, they can only respond so fast. And then they do have a minimum point. Any plant goes so low, and then it becomes a little bit chippy, and it might dump off. And of course, once they do go off, it's not it's not like starting a car. They're not going to just run right back up and run. They can be hours to start. You've got to purge all the fuel out, so they're not going to have a little problem when you try firing up. And then it's a very slow process with the differential expansions, getting the things up to temperature. So there's this startup time and cost that's added into the picture. This is an LM6000, similar. I just got it off Google, but it's similar to the one we have at North Pole at the expansion plant. This every 747 has 4 of these things under the wing. And this is actually only the middle point, because all of these things are referred to as the package, and the package is a relatively small box, and you just can't get far enough away to get a decent photo. So, to explain this, our load following plant, this combined cycle here, basically when you're off at this point, you put in 30% of your fuel before the plant will sustain running. That is the cost of driving the compressor, making the system work. You're not getting anything out for 30% of your fuel. So I suppose you could claim this was negative efficiency down here. But if you're going to run a 50 megawatt gas turbine at 10 megawatts, well, that's about the efficiency you're going to get. It's going to be pretty well down there. So, for example, at half load, which is 25 megawatts, you're using 65% of the fuel. It only really gets up there when you get to the higher loads. Now, we use the heat out at the back end of the gas turbine that normally would have been blowing off to atmosphere, and we use that to heat steam to drive a steam turbine. It has a starting point that's pretty well up here. That you can see it can achieve about 12 megawatts. These are nominal figures because the ambient temperature, for example, if it's 72 Fahrenheit outside, we can get pretty close. We can get to 45 megawatts, something like that. Once it gets to 80 degrees outside, the air is less dense, and it will be 36 megawatts. You know, it drops precipitously for a few degrees at the high end. At the low end, we can, because the cold air is dense, you know, it's already compressed. We're not compressing it, you know, so we get a big advantage from using cold air. So here's our efficiency, 52% with the steam turbine. So that's the basic concept of the gas turbine. So we are using this to load follow Eva Creek. Now, just as a real example here on November 20th, that was the day I was making this slide, so that's why I picked it, but it was 30 below, and we were getting 66.5 megawatts out of this, 4.5 more than it can theoretically make out of this unit, 65 gallons a minute of naphtha, and a 52% efficiency. That's absolutely ideal. But if you load follow Eva Creek, you know, if Eva Creek was a full load, then it would push us down from that 52% down to 33%. You know, so we really take a hit on the efficiency of our gas turbine by load following. And it's the same with any plant. Any plant is a combustion plant is at its maximum efficiency when it's absolutely flat out. And that's where they like to stay. You know, they do not like to be messed with, particularly coal plants. You know, there's a lot of expansion and contraction of the different components in there as you change the temperatures, and they work best if you just run them and leave them running for as long as they'll possibly go. When you start changing the load, they have a tendency to trip off, and once you have tripped off, you find out that some of the things that are needed to start the plant mysteriously stopped working in the last 3 months, you know, so then you have this mad rushing around trying to figure out what's wrong and why, and, you know. So now if we compound this by the grid load, means that this is as high a load that we can take the gas turbine, because, you know, we don't need any more power than that. And then we get our 24 megawatts of wind power. Well, that dumps us down here. Well, we start the combined cycle plant on Jet A, and then we convert at 15 megawatts to naphtha, which is much less expensive. And below, you know, so that magic number, all of a sudden it gets more expensive because we have to drop off a naphtha. We can also run for only a certain time for permit conditions, you know, that the plant wasn't meant to run on, isn't permitted to run on Jet A all the time, and it's different carbon monoxide, different gases come out that we don't have with either naphtha or LNG. So in this area here, the plant becomes unstable. The controls start bouncing around because the plant was actually built as a base load plant to run a full load all the time. And when you push it right down, it gets a little unhappy. This is that curve. You can see the different controls, the boiler feed pump, water flows, you know, all of these things. They're all watching what the other ones are doing, and they're opening and shutting and opening and shutting. And here we took the plant below. Normally this black line, we would have tripped on that line. It went just a little bit below it, and then it bounced back up. But we get pretty delicate at that point, and if we had dumped the plant, it would have been carried by the BESS for a while, the load, but we would have been frantically trying to start something else. So back to look at that same chart again. The deal is that when we need more power out of the combined cycle plant than we can produce, we've got no other choice. We've got to start a second gas turbine. And of course, that second gas turbine will be running at a low efficiency because it's not producing much output. But that's our only option. Then here, where we can't get the gas turbine plant to go so low, we have to curtail wind. It means we have to pitch the blades on the wind farm and intentionally let wind go by, and it's, it's wasted. It's a very sad thing to do, but it's required for the stability of the grid. Let me see, no other inspired conversation there. So if I dig out the production again, the red parts on the top of the chart are the curtailed. It's the energy that we lost by having to let it go in order not to trip the plant. And that's what takes us from 33% capacity factor up to the 34.5. That's the magic difference right there. And of course, 34.5 is exactly what we were predicted to produce from that plant, the wind plant. This is a SCADA screen that they would see in the dispatch center. And when they're getting concerned that we can't take the combined cycle plant any lower, they will force a curtailment on. So here we were at full load on the wind farm and we dropped it to 20, and the plant still wasn't stable, and so they dropped it another 2 to 18. But of course, while that was going on, this green line is the wind velocity, and of course that dropped. So there got to be a point where we weren't actually losing anything, because at 18 was all it was going to make. But you can see here, in my chart that I invented, I had nice broad changes in the wind speed, but this is what's really happening, is the energy is bouncing up and down because of changes in the wind. We don't see it very well on this green line, but you do in the energy produced. And we can have swings of 20 megawatts in just a minute or so. So it does make for a difficult situation, load following. So there are things you could do to assist with load following. And the ideal thing is you would have storage of the power. You'd be able to store that wind power and then take the power out at whatever you set the dial to. And there are methods for doing that. There's pumped hydro has been used for years for particularly in countries where they have a huge difference between the night and day load. I understand that France, they turn everything off at night, and they use, down 12% of the peak in the daytime. So you're talking about power plants that've got to turn off at night and start them up again every morning, which is tricky. With us, our low is about 120 and our high is about 180 megawatts. So that's our range. And so what has been used is pumped hydro, where when you use that power at night when you're not using it to pump water up to a high lake. And then during the daytime, you keep the power plant at the same output, efficient output, a maximum output, and the water runs back down and through a hydro generator. You can also use compressed air storage, which you can put in pressure tanks, but the ideal situation is underground caverns, big underground caverns that you could pressurize. Some places have them and we don't. So, and batteries, not batteries like we have at the BESS, but flow batteries where you would charge up a battery and move that electrolyte out into a charged tank, and you just keep on doing it. So one battery just charges up an enormous amount of electrolyte, and then you let it flow through and you discharge, get a huge amount of energy out of one battery, whereas a conventional battery would discharge after a short amount of time. But all of these things, pretty well significantly more expensive than the wind farm is. So that's desirable, but there's not been an economical way of doing that so far. Another system is load management, which would involve smart grid type technologies that you could perhaps put storage heaters in homes. So at those times when you were curtailing wind, you could instead keep that power and push it out to thermal storage heaters. So you heat up a mass in an aluminum block or whatever in a heater in a house, and then use that heat the next day, and that's a perfectly viable idea. Otherwise, you could manage the load using a pretty expanded SCADA system that could reach in and turn off your hot water heater and your clothes dryer and things like that, so that you weren't using the loads when you really wanted to avoid it, and you could apply the loads when you were okay with it. And the intention would be to take all the power you could from the wind farm as it went up and down, and then when you had a gas turbine on, it would be full on and at the maximum efficiency, and when you did not need it, you would turn it completely off. And there are generation options too, that you could put in incremental generation. And this would be where you have these small diesel engines that produce maybe 5 megawatts. And the deal with them is they can be very efficient. But like all the other combustion type engines, they will only be really, really efficient when they're at the very maximum output. And so the idea is that, you start one, and then you load follow with the second one, and this one's at its maximum efficiency. If you're using 4 of these things, then 4 of them will be at full load and maximum efficiency, and you just take the incremental hit on, 1/5 if you've got 5 of them. And that's actually being practiced in places, but you really need to add this sort of generation when you need more generation, and right now we have quite a bit. We have so much generation because we have a very small intertie line connecting us down to any other source of generation. If you were in a town, in Oregon or someplace, you'd have feeds from different locations, and you wouldn't need all these power plants because you would just swap to a feed from another place. But we just don't have that. With our intertie is pretty well maxed out at less than 80 megawatts. So this is a typical maintenance report. We get these every day, and we can see, like on a Sunday, we started getting slippering faults on this WEC 16, Wind Energy Converter 16, and here on Monday, there they are working on it, and they take care of anything that would cause the unit to go offline and hit their availability, because they have availability guarantees, So, but then if they're not having to do anything which would affect availability or reduce output, then they get on with, they found out that the ladders were a little bouncy, which I would have to say is extremely disconcerting as you're 200 feet up in the air. And so they rigidized the ladders, and then once they're having done that, they had to change the guide system for the fall protection. The Lotto is lockout tagout safety procedure. OSHA Lotto permits have to be reviewed every year, so they're just going through the process. The larger maintenance items, we burned the slip ring on a generator in January, which I imagine was probably a defect from the factory, and that was covered under warranty. And then we had 2 issues with just a little contactor out of the frequency converter, and then this, about this size, choke, looks like a transformer, both on the frequency converters. And both of these things are extremely low risk of failure, and, well, we stuck one now. So we found that we had no real expectation that we were going to have to spend so much time and money keeping the road clean. There's 11 miles of road running up to the top of the hill where the wind farm is, and then another 6 miles on the top. And so we started out with a 1-ton truck with a plow on the front, and that got stuck on the second week. So we got a loader with a bucket and a plow, and it just couldn't clean it in time. So eventually we ended up with this Rollba. It's a Swiss blower, snow blower, and the deal is that we had the contract loader mount snow blower, but we have a pretty good camber on the roads, and they're pretty steep. They're up to 10% grades on the roads, and the weight on the front meant the back end would slide, and they would just slide right off the road. And so this design enabled it to stay on the road. It's much better balanced. And it also is pretty quick. It's got more than 3 times the engine of that loader. They're both the same size, but it can go up the hill and down the hill easily in a shift. And if anybody was injured up there, you have to have resources like that. In the summertime, we can get helicopters and things, but in the winter, they're pretty scarce. These things are delineators, Dalton delineators, as used on the Dalton Highway. And they stand back off the road, and they're pretty high up. A snowplow will go right underneath them. But we found out that the road has pretty good ditches on both sides, and the snow would blow right over the top and just make this nice, flat, smooth. You would have no idea where the road was. You'd creep along on it and put a wheel off and creep along, and it was not fun. So we put these delineators in, and at least you know where the road is now. And it's something that's taken quite a bit of expense and effort, but there's no other choice. These are the sort of screens we see in SCADA for monitoring. You can press on any of these blue things and drill down and get more information. This is for the whole site, so it shows each wind turbine in the location. And if it goes into alarm, the colors change. And it produces little graphs, and you can click on anything and get more information. We're in the second year of a bird mortality study, and there had been a study on the intertie which suggested there would be quite a bit more losses of birds than there actually have been. Only 4 birds, a ptarmigan and 3 songbirds. There's no raptors or large birds, and we had the testing for the scavenger rate, and because if a bird is hit and lands, a scavenger will come and take it away. So how do you know it was ever affected? Well, if it hits the ground, it will leave feathers, and the feathers can identify the bird and what size and type, and so we haven't found any of that. And the observers are tested by putting frozen ducks down, and they found most of the test birds, and this study will continue on this year, but it does look pretty promising so far. And we have some related projects. There's some MIT guys want to put this flying guppy in. It's not a out-of-shape photo. It's actually wider than it is tall. And this is a balloon-mounted wind generator. That's a 30 kW wind generator that's in the middle there. And one of the things they need to pick up information on is what sort of icing this would pick up. This thing unravels from the trailer and can go 1,000 feet in the air. So if you have pretty mild winds, it would pick up more than anything else. But the deal is they lower it down. If it drops off a little output, then they put it back up a little bit, But if it will generate full output sitting right on top of the trailer, then that's where it sits. So because we have that array of wind turbines there, which we can tell what the icing is for all of those, that gives them great information on what the icing would be on these. And, they would be much larger, the final production models. And next month, the state is, I think it's next month, pursuing some LiDAR testing, the laser detection of wind velocity and also turbulence on the front face of the turbine. And the view is that it might be detailed enough in time that you could do a microcontrol of the turbines and change individual blade pitches at points for different points on the rotation to maximize performance of the wind generators. So it's we'll see where that goes. This here, the farmer spread fertilizer a little too close to the tower, and 4 times the generation, there's only a bag of fertilizer. So, and that was about 2 weeks ago when we were having a bit of icing up there. So that's the talk. Thank you very much. And By the way, I'm deaf as a board, so we're going to ask if anybody has any questions that either use the mic or use an interpreter.
Very good. Paul, we'd like to thank you very much. Max here has a microphone, so if you have any questions, just raise your hand and let Max come to you with the microphone, and we'll take it from there.
I'm interested in the bird mortality aspect of this. Every time I've ever seen a wind farm, you can see the things going around. They don't seem to be turning very fast.
Yes.
And how can it possibly strike and kill birds? It just doesn't seem like it's.
Well, it's, the 92 meters rotor diameter, the tips are turning pretty quick. I mean, there's the early wind generators that went in were of a lattice design, and they would offer perching opportunities for birds, and so birds would go and land right on them, as a place to sit. And then the generators ran as fast as they could, and the birds couldn't see them. So there's been a number of design changes over the years that now there's no perching opportunities anywhere on that thing. Well, I suppose they could sit on the top, but also they go much slower. The average wind turbine now, larger wind turbines, they run between about 13 and 21 revs a minute, which is pretty slow. But the birds can see them. I've watched there have been raptors in the area up there, and I've watched them, like this, and they've seen them and flown around. The difficulty is if you get any like teenage, the sort of kid that you would not take in a glass shop, they're less they're more likely to be excited about something and not pay attention to where they're going. So they would be the ones more at risk.
Thanks very much. I've watched Golden Valley and wind for a few decades now. There was a little wind experiment near right off the highway for a while, and there was so much wind that actually delaminated the blades, and it didn't help somebody was taking pot shots at it. But this is quite a bit different and kind of exciting. Trying to manage these sorts of things, I really do empathize and have a lot of respect for people who can dispatch this sort of stuff, and trying to balance all these things. I think one thing that would be helpful in your presentation would be, and you kind of touched on it a little bit, is the time to start various generation plants up, and the time basically to shut them down, and to kind of see an idea on efficiency basically at full load and at the approximate load that they end up running most of the time, and kind of trying to balance that out, basically trying to, in a sense, simulate some of the more micro stuff that the dispatch folks have to go through. One of the suggestions that I had made to both the MAC committee and the board 2 years ago was a way of doing price signaling, and it's also kind of a load signaling as well, to have people voluntarily be notified if it looks like we're going to have to buy more expensive or generate more expensive power, to find a way. There's lots of different ways of communicating to people. That says, look, looks like we're going to be having to do something pretty expensive in the next 24 hours. If you can reduce for that for a period of time, that might save us. And 2 years later, the MAC said they didn't see that was of any advantage, and the board's been wrestling with it for about 9 months, waiting for the report. I'm hoping that situations like this can help make that option available. It's really a relatively low-cost thing to notify people. And the other thing is that there are some large consumers on interruptible power, and normally it's interruptible power is if you've got a major crisis and you've got to shed them. However, in the situation where you have to buy more expensive power and you still have those loads up there that are interruptible, is there some way of building that into the equation? That's really the crux of my second question. Thank you.
Is that it? Okay. Okay. So I'll start with the last question first. The interruptible, actually, we do have interruptible sources or users of power out there. The Fort Knox gold mine, You know, they have some very big motors, and there have been times when we've called them up on an emergency basis to shut one down because we can't supply enough power to keep the lights on for everybody, and they have always done that. You know, and it's been minutes, you know, but it's been pretty quick response. So we have that to some degree, but we don't have, you know, it's a pretty small system, and there aren't many people with those big giant motors knocking around. But they've been very cooperative so far. What was the first one again?
Price signaling. Price signaling.
Oh, the times for startup. Well, the old gas turbines, the simple cycle gas turbines, the frame 5s, they start up in about 6 minutes, from 5 minutes. There we go, 5 minutes. I correct them. Thank you. Correct me anytime. That's good. And it really changes based on what's going on in the other plants. A coal plant can be, you know, a couple of hours. It's depends on what they've got happening and what the temperature is. Any update? 2 hours? Good. I can hardly remember after all these years. I used to be down at the coal plant, but it's been a long time. I worked there for 11 years, but it was 12 years ago. So. Then
And the other was relating to price signaling and how that might be dispatched
Yes.
out of.
Well, that seems to be more of an equation of the modern communications, and it seems like that would be quite approachable these days. And the closer we get to the smart grid, you know, the more we would be able to, you know, voluntarily or even, you know, automatically move that way, if I've got that right. Yep.
2 questions. First, how much of a consumer is the North Pole refinery, the Koch brothers refinery, and then a second question after that. But how big a demand do they put on the system?
You know, I wasn't really in touch with that, but I heard bandied around in the last few days that we would be losing about 7 megawatts of sales to Flint Hills. So they'll still be using some power, but not any of the large pumps and different things that they've got there.
And then the other question is, I do see the threat as kind of fascinating, this icing thing, and you know, remember the mid-November incident to have been a pretty significant one that affected several substations. I've never found out where they were, but obviously there were memorable events for us. But there have been several icing events you mentioned, a second one in November, another in December, and so forth. So could you kind of describe what happened down there in mid-November? Did that substation go out, et cetera? Just add details about icing events over the last several months that we might remember and relate to there at Eva Creek relative to our experiences here in Fairbanks.
Well, related to the wind farm, the icing down there was actually removed from the site. That we have to have communications with the site to be able to run it, and communications and control. And what we had was we have a microwave system that feeds. There's the Kobe Tower by the end of the Rex Bridge there, and that local power grid was knocked out by trees falling on the line. We have about 8 hours of backup battery. And so after that 8 hours is up, we attempted to get a generator down there and were unable to get that hooked in. But the wind farm was down because of lack of communication rather than icing on the generators themselves. In those high winds, it's usually quite warm up there at that elevation. It's about 3,000 feet. And so, you know, the icing is at a different time when you would think. Yeah.
And similar subsequent icing events were generally off-cycle from the Fairbanks icing. In other words, the elevations and so forth were different, and the distance and the weather patterns there is so different from the Fairbanks weather pattern. Is that what I'm getting?
Yeah, appreciate you spinking it up. That's good. Didn't need the mic. That was good. Yes, yeah, it's quite different than Fairbanks. And I mean, I lived in Healy for a long time, and you know, I'd fly into Fairbanks. It was 39 below, and it was 10 above down there. You know, that's pretty common. And then at those elevations, it's even higher again. But the icing, we had some warm weather recently, the endless warm weather that came along, and just as that was going away, we were thinking that was great because it completely de-iced those things. There was a kind of ice storm down there that put more ice on them than we had ever seen before, and we haven't really recovered from that yet. The ice is not coming off in sheets. It's kind of eroding away from the edges, and all of those machines are running in imbalance right now, and we just run them up till they complain, and then we back them off a little bit till they don't, and it's, so we're getting some generation. But, sometime there will be a warm day and all of that will be gone like that, just an hour or two, it will be completely gone, and then we'll be back at full load. But this is it's been a couple of weeks like this, and this is our longest icing experience. But so we could obviously have different ranges in the icing and how it affects us. Sir?
I got 2 questions. One, I didn't see the Aurora Energy Plant in your hierarchy, and I kind of wonder where that falls in. And my other question is, aren't we a partner in Bradley Lakes? Can't we load follow with Bradley Lakes? I know Chugach is probably doing that with Fire Island, but can't we get some benefit out of that?
The deal with Bradley Lake is that we can't always gain access to the power because of the intertie connections down there. And so we can't load follow with that because it's only available in chunks here and there. And Aurora is just part of the blue, as a given that it's in the blue. They run a base load, I think, most of the time. Is that right? So
I just wondered cost-wise, where are they in that stack? You had, Bradley at the bottom, Anchorage Gas, and so on. I just wondered.
So they would be close to the bottom.
Okay, thank you.
I have a question on the economics of this project. So you've got a year of operation. How does it compare to what you projected, and what do you see in the future?
Well, it takes quite a time to crunch the numbers for the year, and I haven't seen exactly where that's taken us. Excuse me a sec. But it seems like it's pretty close. But one thing you should realize is these things vary a lot from year to year. And so, we really need 5 years of data or 10 years before, you would have a more sound solution, idea of those numbers.
So far, no big surprises.
No, it's pretty close. And the production is right on. The availability was good. If you were off on production or availability, then that would be a cause for concern. But we haven't been. So.
I got a maybe a solution for your icing problem. Have some kind of weight sensor that would sense the weight gaining on the blades, where it would automatically kick on a heating element in the blades to throw the ice off.
Yeah.
And about the predator problem, some kind of fence to eliminate the food source for predators around the facility.
Yeah, we do actually have a plan to mow down different areas at a certain time of year to stop the birds nesting there. Yeah. This thing is 6 miles wide. Yeah.
About it would automatically kick on, reach a certain weight,
And
use its own electricity to heat it up.
And the heating elements in the blade wasn't actually offered, and as far as I know, it still isn't.
It's all it takes if you find heating layers, run down the length of the blade to throw the ice off.
Okay.
If you have an icing problem, why is everything painted white?
We did consider that the blade should have been painted black, and there was some reason which I was not privy to that caused that from going into fruition. I think the icing expectations are mostly when it's dark anyway, and so but I couldn't help but think it would help.
Yeah. And then second question is, how does this plant compare with other similarly sized plants in the lower 48? In other words, the numbers here, how does it compare to a similar installation of same size?
I haven't actually looked at any other facilities of the same size. I mean, we've compared ourselves a lot with the much larger Canadian one because they have icing, and their icing problems are a lot more severe. I mean, they say that our icing is somewhat better because they call it high and dry. You know, it's at a high altitude and it's not a really wet environment, where the Canadian one is closer to the sea and the ocean, and they pick up all kinds of icing, so they lose a lot of production.
You said Eva Creek produces at 8.7 per kilowatt hour, and does that include the cost to chase? Is it called chasing or load following?
No, it doesn't.
What is the cost of load following in kilowatt hours?
I don't have a number on that, I'm afraid, but it doesn't. The 8.7 cents is exclusive of the load following cost, and you know it changes a lot. You know, because you know the efficiencies of the units as they go up and down, they've got a different cost for every second that they're running.
So some of these wind turbine plants have already gone through their life. Seen some abandoned wind turbine plants in Hawaii, especially. What's the predicted life of these turbines?
Oh, it's up to 25 years for the nacelles and rotors, but the tower would last, you know, much more than that. So most of them are reviewed for about the 20-year period on. They're checked for repowering if there's a more efficient way of doing things, or you know, if there were heaters in the blades and this sort of thing. You know, technological upgrades where there would be payback.
You had a lot of power oscillations with changes in wind. To smooth those out, have you looked at flywheel technology? Isabella used to have one to smooth out their drag lines.
Oh, flywheel technology to level off. Yeah, the deal with that is it's good from now for a few seconds from now, you know, but it is on the list of a way of balancing your load. You know, I mean, they use the flywheel because they generate power when they swing out, and they use power when they pull in with the big ace in the hole, the whatever that thing is. And so, yeah, it's a very short cycle time relatively. You know, what we need is something that saves power now for 7 days, you know, something like that. I mean, it would be unreasonable to expect to sort of save power now for 2 months from now or next year.
I was thinking that like the weather conditions might be appropriate for some kind of solar alternative, because you know, when it's windy, you say it's windy a lot in the winter time. We may not be that much sun, but I'm just curious, do you have any kind of idea about having any solar collectors or solar generators?
A solar array somewhere.
Yeah.
Yeah.
Perhaps at the same site. I really don't know.
Yeah. Well, you know, I think solar has, you know, good applications on individual houses, you know, but for utility, you know, we have the bulk of our load is in the wintertime, you know, when the sun's not shining. You know, we would have to have an inordinate amount of solar to even put a dent in that, and then in the summertime it would be more load than we could use. So it's you know, if you were in Arizona, you know, where the sun comes out and your air conditioner goes on, it's the perfect relationship, you know, but for us it's kind of the other way around.
Well, like you mentioned before, underground chambers, caves, I've been involved in the mining industry. Miners are willing to do that. They do it for oil reserves all over the world. You can go down, blast out, cut out any size chamber you want. If it's hard rock, it can be done. So probably get some foreign company to do it over. That's an idea as far as storage and with the dams and that. There's usually a lot of glass.
Okay, thanks. Oh.
Any special earthquake precautions? foundations?
The foundations were designed and overseen by PDC, the local Alaskan company, and we thought that was a good idea. But to meet the requirements of the area, because there's this enormous upside-down mushroom of concrete underneath the 190-some tons, but also pilings below that.
I have a question. Paul, I'm up here. I don't have a microphone. Thanks for being here tonight. I wanted to ask about the effects of Flint Hills Refinery closing down on your naphtha fuel supply for the power plant out there for load falling.
Yeah, it's not really the Eva Creek question, is it?
Well,
But
because
it's
for
one
load
that
falling, I guess it is.
it's one that we don't have. They only told us that they were doing this so recently, and we've initially, I think that they said that they would be able to carry on supplying naphtha, and now aren't. So we are trying to figure out alternatives. The plant can run on other fuels. It's got to run within the permit, and it's got to not damage the plant. There's catalysts in there. It's got CO reduction catalysts that if you put any quantity of sulfur in will destroy those. And so, we're looking for the right fuel and, if possible, the right price. But in the long run, what we really need is to run on gas. We know the gas is cheaper. It's just if we could kindly get a pipeline or a trucking system in place, then we can definitely use it. And it would have to be vaporized, or not liquid, but natural gas. So the unit can start and run all the way up to full load on natural gas, but it would be more benign environmentally and also less expensive, so benign on our pocketbook. So yeah, the sooner we get the gas, the sooner we'll be a little bit happier. Oh, well, thank you all for coming. That was most entertaining.